Hello, everybody. Welcome to the H&H Best Practices presentation um, by the DER Restoration Partnerships Program. I'm Robert Kearns, the Restoration Partnerships Coordinator. I join along here with folks from the Partnerships Program, as well as GZA and all the different partners. We're really excited to and thankful to GZA for helping put this presentation together. And this presentation, just for everybody's knowledge, is that it's funded by the Resilient Massachusetts, Resilient Mass funding, capital funding. And we're really excited to offer this to help build capacity for climate change resiliency in our communities. And we've listened to the partners, you all in the nonprofits in the partnership program, and seen that, H&H is something where there is a need and an interest in getting more information and more knowledge. So we're hoping that this presentation can help you all in your project management and also to expand the knowledge to other practitioners as well as city and town officials and the like. So we're really excited for this training to help build capacity. And just for everybody's knowledge, we're really grateful to Courtney and the Berkshire Regional Planning Commission for hosting and recording it. So the recording will be made available to everybody as well as the slides after the presentation. And GZA is going to have a great presentation for about an hour, and then we'll have time for questions and answers after that. So we're really excited to dive deeper into H&H. I know you all are working on it from dam removals, culverts, bank restorations, and the like, and we're really excited to get this going, get more information out there, and also expand on other trainings that have been offered by the Commonwealth and just use this to help all the work. So with that, I'll pass it off to GZA and Courtney, if any other information.
Great, thank you. So I think let's get started. Welcome, good morning, welcome to H&H 201, what we're calling Understanding Models and What They Can Tell Us. Today's program is going to be presented by folks from GZA Geo-Environmental, and on the next slide you will see those folks. And the next slide will be soon. There it is. We're going to get our legs under us here. So I am Chad Cox. I'm a professional engineer, a civil engineer with a specialization in water resources and a senior principal with GZA. Today I'm going to be joined by Jennifer Burke, also a professional engineer and a senior project manager with GZA in our Springfield office, and Rex Gamble, a water resources engineer and a really crackerjack modeler, both from the hydrology and the hydraulic side. And he's going to do a lion's share of the presentation today, talking about the technical aspects of modeling. So just a quick word about kind of our objectives today, what we're hoping that we'll be able to convey some increased understanding of. So we're going to start with a very short review of some of the basics, kind of typical H&H terms and concepts. And then we're going to hope that at the end, you'll understand the difference between a hydrologic model and a hydraulic model, understand kind of different storms and floods and how those get described and how they get used in project design. We'll be talking about typical H&H modeling software packages and their applications, helping you up to understand some of the key considerations in developing a scope of work that you might want to put out to bid for projects that you are advocating for, and then how you can interpret H&H model output that you might be getting back from people that are doing modeling for you. So this whole presentation we're calling it 201 because it builds on an earlier webinar. We've got a link to that earlier, more basic information webinar in this slide. It's on YouTube. And as was mentioned, all of this material is going to be provided to everyone that's on the call now after the session, so you don't have to worry about scrambling to take a lot of notes or do screen captures or something like that. You'll get all the native documents after the program. So let's dive right into it. The first thing we're going to do is really just answer our basic question: what are the H's in H&H? The first H is for hydrology. It's important to understand today we're going to really be focusing on surface water hydrology as opposed to groundwater hydrology. Both are types of hydrology. We're going to talk about surface water hydrology for the most part today. And that tells us about precipitation and runoff. It really then focuses from an application standpoint on the amount and timing of stream flow. How do we understand how rainfall translates into runoff, and then that translates into stream flow? The second H is for hydraulics, and that is more about the characteristics of that stream flow. Once we know how much water there is in the stream, we'd like to know things like, well, what's the depth of the flow? What's the velocity of the flow? What are the peak water surface elevations that we might expect a flood to result in? So H&H, hydrology and hydraulics. Let's go to the next slide. Our most basic sort of concept in hydrology is that of the watershed. So that's an area of land that drains all of its water, all of its liquid water in the form of either direct precipitation or runoff or snow melt. It drains to a common point such as a river, a lake, or an ocean. So any point along a water conveyance system, a stream, a river, whatever, any point can have its own watershed. It's basically just the area uphill that drains past that point. It's also known as a drainage basin or a catchment area, and the boundaries of a watershed are defined by the topography of the land. So back in the ancient days, we used to sit down with a USGS quad map, and we would sketch out the limits of a watershed by tracing along topographic ridges and divides to delineate the watershed. And then we would take our planimeter and we would trace the watershed boundary and find the watershed area. And, for those of us who did that, that was a sort of an arduous but rewarding task. These days, it's done with the click of a button on a computer program, which Rex will talk about later. But the concept of the watershed remains the same. All right, let's go to the next slide. Rainfall, another basic. Obviously, rainfall, precipitation, that's the driver of water in streams. So knowing about rainfall, knowing the characteristics of rainfall is fundamental to the science of hydrology. These days, it's actually pretty easy to get a basic understanding, actually an advanced understanding of the kinds of rainfall that one can expect in any particular location based on what you want to understand about it. Are you looking for typical rainfall? You're looking for stormwater rainfall. When you're thinking about storms, the most common way to be thinking about precipitation amounts is through the use of the NOAA Atlas 14, which is a online tool from the federal government where you can pick any point on a map and point at it, and it will generate a point precipitation frequency estimate table for you, and also curves and that kind of thing. But the table is actually very helpful, like you're seeing on the lower right of your screen. And it will tell you the expected amount of rainfall based on a particular duration of a storm and based on the recurrence interval of the storm. So recurrence interval, the sort of annual chance of a particular storm, a particular rainfall amount happening, is an important concept in hydrology and hydraulics because that is telling us what are the likelihoods of a particular event happening in any particular year. Often we will talk about storms or floods with respect to their return period, a 50-year storm, a 100-year storm, but that is also a proxy for its annual exceedance probability. We'll talk about it a little bit later. Let's go to the next slide. Once we know something about our watershed and the rainfall falling on our watershed, then the next basic step in hydrology is the transformation of that to runoff. So runoff is the portion of precipitation that flows over a land surface as opposed to it being captured or otherwise infiltrated into the soil. So runoff is what's going to ultimately drive flood flows in our water bodies. The amount of runoff that we can expect is driven by the watershed characteristics. So the size of the watershed, the type of soil that makes up that watershed, and then the land uses within that watershed. Is it farmland? Is it forest? Is it parking lots? And of course, runoff is directly related to precipitation, both intensity and duration. Let's go to the next slide. The basic tool that hydrologists use to think about the transformation between precipitation to stream flow is the flow hydrograph. And that's a graphical representation of flow rate over time at a specific point. There's also a stage hydrograph, but that's more of a hydraulics thing. We're going to talk about flow hydrographs right now. And what it does is lets us visually represent and consider how a rainfall event, and you can see in the left-hand graphic, the rainfall is depicted in the blue, and those are discrete amounts of rainfall over discrete periods of time. And that rainfall is by means of a hydraulic model or otherwise transformed into runoff, which is the linear curve there that represents the flow rate hydrograph. And the rainfall turns into runoff. The rainfall is measured typically in a depth. The runoff is measured in a flow rate, which might be volume over time, such as cubic feet per second. And you can see the rainfall in a real storm starts, peaks, and then drops off as the storm ends. And that results in the stream flow in your river doing essentially the same thing. A rising limb of the hydrograph, a peak discharge, and then a falling limb. And then if you're interested in total volume, you integrate under that curve to get the total volume of runoff. Every watershed will have its own characteristics that influence the shape of the hydrograph. As you can see on the figure on the right, a rural watershed that perhaps is highly vegetated, lots of forest land, that often will result in a kind of low and flat hydrograph as water is slowed and infiltrated, as opposed to a more urbanized watershed with lots of impervious area, which results in a steeper, flashier hydrograph, as shown on that the peakier hydrograph on the right there. All right, let's keep going. So the other important tool in a hydrologist's toolbox is statistical hydrology. And statistical hydrology makes use of directly collected stream flow data. That is generated by the stream gauge network that is maintained by the USGS and others, which is measuring flow rate, often on a near continuous basis, and generating data sets over time that can be then statistically analyzed to create flood frequency curves that will give us a way of understanding the probabilities of a particular flood of a particular flow rate occurring in any given year. So we're transforming data about flow rates into statistical information about the likelihood of a flood happening. Let's go to the next slide. So again, here's a sort of a easier to read image of that flood frequency curve. A curve like this can be read by understanding what is the flood return period that you may be interested in, given a particular design criteria or a risk tolerance. So up on the top, that's your return period. And then you go down, you intercept the red line, and then go across to the left, and that gives you your flow rate. At the bottom, you'll see the probability. So as we touched on before, return period is another way of talking about annual exceedance probability. It's the inverse of that. So a 100-year flood is a 1% annual exceedance probability. A 5% flood is a 0.2% annual exceedance probability. The higher the number of the recurrence interval, the lower the number of the annual exceedance probability and the larger the flood. The reason hydrologists tend to prefer to talk about annual exceedance probability as opposed to the sort of more easily understood return period is to emphasize the point that that's an annual idea. Just because you had a 100-year flood this year doesn't mean it's going to be 99 more years until you have that same flood. The probabilities kind of reset every year. You could have a 100-year flood this year, and you could have a 100-year flood 6 weeks from now. It is a probabilistic sort of issue. The likelihood is low, but it is possible. And so thinking about it in terms of risk and thinking about it in terms of probability, I think is helpful in many ways as we think about these flood events. Let's move on. That data, the flow data that's been collected over many years, has also been used to create regression equations. Regression analysis is a way of taking the basic characteristics of a watershed, in this case, and creating formulas that can be used to relate those basic characteristics to a parameter that we're interested in. Most typically, that might be something like the peak flow rate of a flood of a specific return period or annual exceedance probability. Lots and lots of highly technical papers have been published to create these regression equations. Back in the day, we used to read the papers and do the math by hand. Now that math gets done easily through, again, the online statistical programs such as StreamStats that Rex is going to be talking about later. Let's keep going. So now we're going to move from hydrology to hydraulics. Hydraulics, again, the characteristics of the flow once they are in the conveyance that they're moving through. So the most basic type of flow that we often think about in hydraulics is open channel flow. So that's flow through some sort of a channel, whether it is a river channel or a culvert or a half full pipe, but that flow is flowing in such a way that the top of the flow is open to atmosphere. So it's not pressure flow. It's not flow in a pipe that is full and pressurized. It's open channel flow. And the basic equations that describe open channel flow are really the basic building blocks that most of the hydraulic models that Rex is going to be talking about are built on. The most basic kind of open channel flow is uniform steady state flow. That's sort of easily done even by hand calculations to make those estimates. But as things change, you get to non-uniform flow because of changes in the configuration of the conveyance, or unsteady flow because of changes in the rate of flow over time. Things get more complex, and that's why we have computer models. So let's go to the next slide. We'll sort of expand upon that. Uniform flow characteristics which don't change over time. So you have a long stretch of river. The cross section of the river is about the same. The slope is about the same. You've got uniform flow. The flow through that reach is of the same velocity, the same depth all the way through. But if we start mucking about with that channel, such as if we put a dam in place, then stuff changes and flow characteristics change. And now we've got non-uniform flow characteristics. The depth changes, the cross-sectional, the wetted perimeter changes. We've got weir flow over the dam. So these are some of the things that the models can help us understand. And on the next slide, we can see, the animation that's happening there on the left is a representation of how the flow characteristics, in this case, you can really see depth, are changing over time as a result of the passage of time and that hydrograph on the right being routed through that particular cross section. So again, the great computer tools that we have can help us really understand how things change when we have real world sort of situations. All right, I think the next slide brings us to the end of my portion, and I'm now going to turn it over to my colleague Rex, who's going to really dive deep into the specifics of modeling. Rex, take it away.
Hey all, thank you, Chad, for introducing all that H&H terminology. So one other thing we talk about a lot when it comes to H&H modeling and H&H terminology is 1D versus 2D models. First, I should start by saying that flow is inherently 3D. It's in 3 dimensions: up, down, left, right, farther, not farther, downstream, upstream. But that's very complicated, and it takes a lot of computational power to do all those calculations. So a lot of people a long time ago simplified a lot of these 3D equations into either 1D or 2D equations, which we can now apply in modeling. So let's start with the 1D modeling on the left. Basically, 1D models assume flow is only upstream and downstream. So it's only going in one direction. This basically simplifies the rest, so it's average. So it's an average in the depth and the average in left and right. But when it comes to these models, they're generally calculated in cross sections. So as you can see with the little figure on the bottom left, a calculation is being performed here every cross section, but it's only assuming flow is going downstream. In this case, that's a little bit to the right and down. So when it comes to 2D modeling, models are generally calculated on a mesh or a grid, which you can see overlaying over this terrain on the bottom right here. But these calculations are done in 2 dimensions, which are upstream and downstream, and then left and right if you're looking downstream at the channel. And you can see that in the little figure here. But when it comes to this, the averaged depth is still there. So there is the dimension of depth, but it's all averaged, and there's no difference from the top of the channel to the bottom of the channel. Essentially, 2D models are a little more detail-oriented, a little more complex, and they calculate H&H calculations at every cell interface. So it's a lot more calculations for the same amount of area if you're modeling the same thing as 1D. So a lot higher detail, but a lot higher computation time. We're not going to touch on this too much, but there are also very specialty models out there. So there are models that focus, for example, on scour and erosion around bridge piers and abutments. There are sediment transport models, which try to estimate how sediment moves through a river channel. Those are available and around, but these are very specialty, and they're usually done only in very specific cases. But we want you to know that they're out there and they're available. Hey, now that we've talked about hydraulics and hydrology a little bit, we're going to be diving a little more into modeling and what they can tell us. Essentially, a big question here is, why do we build models? And essentially, I think what we want to say is that we want to answer questions without actually being able to construct or having these things happen. So for example, we want to be able to know what the proposed conditions for this culvert or dam are going to look like without actually having to build it. So instead we build a model. In addition, we want to know how much flooding there is in a certain area without that flood occurring. So we build a model to estimate that. But I want to focus on basically, we want to answer a question. And the type of questions that we usually want to answer, for example, are, is there going to be erosion or scour? What are the velocities? Are the velocities dangerous? How frequent and how hazardous is flooding? And in the case of restoration, a lot of time we're going to focus on fish passage. So is this channel, is this weir, whatever, appropriate for aquatic habitat or aquatic passage? A lot of this stuff or these questions and what you're going to do are limited by how much data is available. Are you only going to be using public sources? Do you have a consultant to make a very detailed H&H model? But you basically want to think about all these things when it comes to your project goals and your scoping. So what are some public data sources that you can consider? There are many out there. Chad's already touched on a few, And we're going to talk a little more in detail about them. We're going to talk about FEMA data that's available, both FIS studies, which are reports, and then the flood insurance maps, which is just a mapping representation of the flood data that FEMA has. We talk about stream stats. We're going to talk about stream gauges that are out there. And then, of course, we're not going to go into too much detail, but you can always look at past modeling and past reports that have been done. So when it comes to FEMA data, it's a very common source you're going to find throughout the US. And essentially, you can search specific communities by coordinates or by community, and you can try and find whether FEMA has this data available or not. We generally break FEMA data into flood insurance studies, which I said is essentially a report showing methodology, showing profiles. I'll talk a little more about that later. And then the mapping itself, which is the mapping of the modeling data that we can look at to see different zones, different flooding elevations. So this is an example of a FEMA flood map. This is a riverine setting specifically. And I just want to point out the different zones that FEMA likes to call out here. So the very important one is zone AE. If you look in the legend here, they essentially indicate that means this has been modeled by FEMA and there are flood elevations available. Zone X right next to it essentially says it could be a flood area. FEMA has not modeled it. In zone A, it's basically saying this is probably a flood area, but we don't have any elevations for this mapping specifically. So those are something you should look out for when you're looking at these FEMA maps, these zones, and whether flood elevations are available. Another very important thing, which you can see in the shading, is the floodway. And if your project is in a floodway, that has a lot of implications for permitting, which we're going to talk a little about later. This is just another example of a FEMA flood map, just a coastal context here. The two zones we have are zone AE and zone VE. Zone AE and VE both have flood elevations available, but AE basically says there's not too much wave action and velocity, but zone VE, which is a coastal specific zone, indicates there's a lot of coastal wave action occurring. So that's just something to look out for when you're looking at these coastal maps. So hopping back to the FEMA FIS, which is the report that all this data comes in, there's a lot of good data in these reports that we can apply. For one, they have all the modeling methodologies that FEMA used for a specific county or a specific community. So you can go in, see how old the model is, if they use the HEC-RAS model, a HEC2 model, what type of hydrology they perform to estimate peak flows. That's all in there, and you should always try and look at those methodologies. But some useful data, we believe, that is in the FIS are peak discharges. So for every AE zone, FEMA has peak discharges for that area. This is an example from the riverine flood map that we were using. We can see that the 100-year flood, which is the 1% annual occurrence chance, has a peak flow of about 5,100. Another very useful resource within the FEMA FIS report are the FEMA FIS profiles. And these are essentially longitudinal profiles, so hydraulic profiles going from upstream to downstream of a river. And these should match what's in the firm mapping. But consultants generally use a lot of this data. It's going to be kind of the standard you're going to compare a lot of models to, especially if you're in a FEMA floodway. And we do use this for input data as well as sometimes for calibration. So another very useful public data source is StreamStats. This is basically a web application maintained and made by USGS. It relies on the regression equations that Chad previously talked about. So essentially you have the web application you go to a map, you zoom in, and there's a bunch of squiggly blue lines. Those are river channels. You can click on any point with the blue line, and essentially the model will delineate the watershed for you very quickly. That is shown, the watershed delineation is shown on the bottom left graphic right here. And then it pulls up a report with peak flow statistics, sometimes base flows, but that varies from state to state. But it's a very useful tool to get a very quick and easy estimation of hydrology at a site. Another very useful tool is the gauge system, the stream gauge system maintained by USGS throughout the US. Basically, this provides stream flow data at any gauge location. Chad talked a little bit how they've done that. But you can go to the USGS website, click on a specific gauge. There's a list, which is the central graphic here, which shows a list of data, daily statistics. Continuous data is also a data type where they have like every 15 minutes. You can see what dates they have from beginning to end. And then you can use that to estimate statistical hydrology that Chad was talking about earlier. We're not going to touch on this too much, but we also want to note that there are tidal gauges around. Those are generally maintained by NOAA rather than USGS. They provide both observed and predicted tidal stages for sites, as well as other statistics like high tide, low tide, mean high water, mean low water, everything along those lines. So it's just a useful tool if you're trying to look at tides and if you have a tidal site. Okay, now that we've talked a little about those publicly available data sources, we're going to talk a little bit more about some modeling intensive, some type of modeling that you might have to get a consultant to do. So we'll start on hydrologic models. There are many different types of hydrologic models out there. We have a list of examples here, but I just want to emphasize that each model type uses a different methodology to estimate their peak flows or whatever you're trying to look at. Generally, there are three types that Chad did talk about. There are regression models, such as stream stats. There are statistical models, which look at gauge peak flows and estimate values based on those. An example of that is the USGS peak FQ and the HEC SSP models. And there are runoff models, which are a little more calculation heavy. But these models essentially try or attempt to convert precipitation values you input into a flow hydrograph that you might have to use for a hydraulic model down the line. Examples of rainfall runoff models are HydroCAD, which is very frequently used for stormwater modeling, as well as TR55, which are essentially handcalcs to do this, and HEC HMS, which is a publicly available hydrologic model, generally focusing on rivers, but this was developed by the U.S. Army Corps of Engineers and is generally the go-to for a lot of riverine modeling. So when it comes to hydraulic models, there are also a lot of available models. Like I said, we generally stick to 1D and 2D models here, and there's also a lot of more complexity when it comes to uniform, non-uniform, steady, unsteady, like Chad discussed. I also want to say that 3D models are around, but it's probably something you never have to do unless you're looking at very specific nitty-gritty type of modeling. But when it comes to hydraulic modeling, like I said, there's a lot of variability in terms of 1D and 2D. HEC-RAS, which is a very commonly used model for river systems, and there's an example of the output on the bottom left, has both 1D and 2D capabilities, while some other models, such as HY8, which is shown on the bottom right graphic and focuses specifically on culverts, only have the ability to do 1D type of modeling. So you have to just familiarize yourself with what type of models you have and where they're appropriate. And we'll discuss that a little more going forward. Again, there are more complicated models out there. For example, this is a combined H&H, so combined hydrology and hydraulics model. This essentially puts hydrology and hydraulics within the same model. You'll also hear these models discussed or talked about called rain-on-grid models. They apply precipitation directly to a 2D grid, calculates the infiltration per grid, and then routes the flow through the grid. Again, these are pretty complicated and pretty computationally complex, but they are becoming more and more common, especially for stormwater modeling. Two common models for this type of modeling are HEC-RAS, specifically 2D HEC-RAS, and then PC-SWIM, which is a stormwater-focused model developed by the EPA, I believe. So how do I choose between all these models? It's getting pretty complicated when it comes to this. So we'll try and walk through this and provide some examples at the end, but there are things you want to consider along the way. So for one, you want to look at your question that you're asking and what output is helpful when asking this. If the output you need is only peak flow rate, then you only need to do a hydrologic model. But if you want to have an output that has water characteristics, such as water surface elevation, depth, velocity, you're going to have to make a hydraulic model as well. And then there are a bunch of other questions that are more appropriate or not. For example, steady, unsteady. If you're looking at flood retention, potentially in a dam or in wetlands, that has to be done with an unsteady model, because a steady model assumes that there's no flood retention, flood change throughout the time period. And when it comes to uniform, non-uniform models, for the most part, most modeling efforts are non-uniform nowadays. Pretty much the only uniform thing you can do are hand calculations, such as Manning's equation, sorry. But it is good to know that when you're modeling, if you have any dam, any culvert, any bridge, you're gonna have to use a non-uniform model. So when it comes to level detail, there are a whole bunch of different ones. For example, 1D, 2D you might want to consider, but that's gonna be, again, very project specific, and we'll talk a little more about that later. We're also gonna be discussing how project application goals, budget, and funding play into your model selection. So to explore this more, we're gonna try and focus in on the results we can get from specific types of models, and you can get from hydraulic models. So when it comes to understanding model results, the first thing we're going to talk about is hydrographs. Chad already touched on this, but essentially, if you're thinking about hydrographs, you want to think about a hydrologic model. Again, we're depicting flow change over time. This is an example of a watershed from HEC-HMS on the left and the resulting hydrograph shown on the right. If you're trying to look for watershed characteristics, a common type of result you're going to get is a hydraulic profile. Basically, it's a visual representation of water surface with space, pretty much. So this is an example on the bottom left of a result from RAS, and this pink line on here is what we're going to plot as the profile on the right. So you can see there's a dam in place here, and that's causing water to back up behind the dam. And then once it gets downstream of the channel, it's a little more straight, a little more uniform. Another type of very useful modeling result, you can get this from a lot of type of models, are inundation areas. This is a 2D hydraulic model example here showing the inundation area with depth over space from a plan view. It's very useful for trying to estimate what's going to flood, what's not going to flood, how deep is it, how dangerous is it. You can also get the same result here with velocity. So essentially you're having a plan view with a velocity plot. You can see as it goes downstream of this dam, speeds up a lot, hits this culvert, and just keeps going pretty fast, around at least 3 feet per second. One thing that's also very useful is a lot of models, especially 2D models, provide particle tracing, which shows, which essentially just shows flow direction as well as magnitude. And you can see it as these little white lines that are moving in this video here. And then one thing you also want to consider when it comes to making models is calibration and validation. So you can make a whole bunch of pretty models and get a whole bunch of pretty results, especially with all the capabilities we have nowadays. But whether this is right or wrong, whether it is within 1 foot of what's happening or not, that's something we have to scope down with calibration validation, if possible. So calibration is essentially the process of adjusting model inputs to produce results that match observed data or real life data. Validation is pretty similar. You essentially have a data set that's independent and you run calibrated parameters to see if it also matches this independent data set. Some publicly available data that can be used for calibration are NOAA storm depths. You can get NOAA gauges around the United States, as well as USGS stream flow gauges that are very useful for calibration. For hydraulic model calibration, you can look at the USGS website to get flood high water marks. So if you're modeling a flood and there's been a historic flood, USGS goes around after a storm and collects what elevation they believe the peak flood was for that storm event. Very useful for calibrating hydraulic models. And then you can also look at known local flooding events. So if you don't have any of this USGS or NOAA data for calibration, you can go to a local and ask, hey, how much did this road overtop during this storm? And it's not exactly the most precise data, but it's very good to know just to hone in your results. So with all this, it's good to check multiple sources, multiple model types if possible, and see what works best. But I should also note that if none of these data is available, it is very hard to calibrate a model. So it might not be possible in a lot of cases. And this is also very common because we want to build a model where we don't already have observed data for the most part. So just know that this is a very useful tool, but it's not possible all the time. So this is an example of a hydrologic model calibration. Essentially, we're adjusting input data to match observed data, as we previously mentioned. We're using a historical storm here that we have rainfall data for, rainfall radar data specifically. The inputs that we're adjusting are shown on the bottom left graphic, and then on the bottom right is our output, as well as the observed results. So from here, we had observed stream gauge data. This is shown in the black, and then our modeling output is shown in the blue. And you can see we calibrated this and changed these inputs so that our peaking is occurring around the same time and at the same magnitude as the observed data. This is an example of a hydraulic model calibration. Again, it's the same process. You model historic storm or historic data, and then you're going to adjust inputs to try and match observed data. In this case, the observed data we have are USGS high watermarks. These are shown in the red with the little red dots on this hydraulic profile graphic. And then our water surface elevation profile is shown with the blue line going through the hydraulic profile. And you can see we calibrated this to try and get this hydraulic profile, so the blue line, to cross any red dots that we're seeing, which represent the high water marks for this historic flood. So we just discussed a lot of modeling and this does that, this does this, but we think it's helpful to do some examples about how to choose a model with certain scenarios. So our first example here is a culvert replacement to reduce overtopping of a road or to stop overtopping of a road. And when you have this, we want to have, what question are we trying to answer, right? So here our question is, what culvert size will pass the 50-year flood without overtopping the road? When it comes to selecting a model for this scenario, you have to use a hydrologic model because you want to estimate the 50-year peak flood inflow, and then you have to use a hydraulic model to estimate the water surface elevations. So for the hydrologic model, there are many different options out there. There's stream stats, which is regression equations. That's not as intensive. You can perform a gauge analysis if that data is available. There's a gauge nearby. It's a little more intensive, but it's still not a high intensity type of process. But you can also make a HMS model if none of these are available, or if you want to get into that amount of detail. These are all valid hydrologic models for this context. So we're going to talk a little more about what else can slim these model choices down. But when it comes to hydraulic modeling, there are still a lot of options. You can use Culvert Master or HYH, which are 1D culvert specific programs, but they are steady programs. Or you can use HEC-RAS, 1D HEC-RAS to be specific, or 2D. Either one's fine. They're all, again, valid choices. The example 2 here is dam removal for fish passage. So with this, the question is, what channel geometry will allow the depth and velocity for a fish to pass this section of river? When it comes to model selection here, we're a little more limited. When we're thinking about fish passage, usually we want to look at seasonal base flows. And the only very detailed option here is to do a gauge analysis here. Stream stats or regression equations don't always provide the amount of base flows, seasonal base flows you want. HEC HMS model generally focuses on flood elevation or flood flows, and gauge flows are just the most reasonable for this context. When you're looking at a hydraulic model, we want to have pretty detailed depths and velocities in the river channel. And we probably want to see how that varies, left to right, as well as upstream to downstream in a river channel. In that case, 2D HEC-RAS is probably the most applicable model in this context. Okay, so we're gonna keep going with model selection, but we're gonna add a layer of complexity on top of that. We're gonna talk about how project stage, permitting and funding plays into that, but Jen is going to take this topic away.
All right, thanks so much, Rex. So I'm the complete opposite. I'm going to be very non-technical in my portion of the talk and kind of get down to the practical of thinking about the different types of projects that you might be helping to get grants for, helping to write scopes for, or starting to do the review process for. And as Rex said, there's many things that can kind of decide for you what you need to do in terms of analysis, depending on the stage of the project you're at, what permitting you know may be required, what review by agencies is required, or what funding you have. You may have different requirements. For example, when it comes to project stage, if you're at the very beginning stages of trying to figure out whether a project is even feasible or what might be involved and to try to get kind of some very preliminary data, then maybe one of the less specific models is appropriate. Also, if you have really low funding for something like a concept or a feasibility study, then that may be a good starting point. And then when you get into more complete design process is where you'd bring in a more detailed model if needed. Another big consideration is who's going to be reviewing this. Is MEPA going to be involved? Is FEMA involved? Or is MassDOT involved? And I'll kind of deep dive into what each of those might mean. And then finally, what is your funding source? Where do you think you're getting the money for this project, for the concept, for design, for permitting, and for construction? Because that may also kind of tweak which way you need to go in terms of an analysis. For example, if you have MVP action grant funding, you'll probably need to consider future climate projections, and they have a specific tool that they'd like to see used for that. And we'll talk a little bit more about that as well. Next, Rex. All right, and this is kind of just more of a visual representation about how some of these things could drive what you're using for your models. If you don't have a lot of time or don't have a lot of money and you're at the concept stage, when it comes to hydrologic models, maybe you're looking at something more basic like using FEMA flows or stream stats or doing a 1D model. But if you are higher in the design, further along in the design process, or you have the funding, then you're probably going to have a goal of looking at a higher end model like HEC HMS or HEC RAS or 2D HEC RAS, and hopefully having funds for calibration if calibration is possible within your watershed and within the stream. And calibration takes time and takes effort, so that is something that will tick the cost up to be on the high end of the spectrum. But we just wanted a graphic to kind of lay out where do these things fall in the context of time and money, since that's what a lot of these projects come down to. And also complexity of the site will come into play too, in terms of what you need for complexity. Next, Rex. All right. So one of the things to think about is whether or not this project will ultimately require MEPA review, or if you may qualify for an exemption. Certain types of ecological restoration projects may qualify for that exemption, and you get to basically skip out on the MEPA process. But if you know a project may not meet that exemption set of requirements and that you may have to go through MEPA review, it adds a different layer of thought that needs to go into scoping. So MEPA can be involved in projects that require agency actions or they exceed certain review thresholds. A big one that comes to mind is there's a criteria or a threshold relative to any reduction in impoundment capacity behind a dam. So a dam removal might trip that. Another one that's a very common one is half an acre of any other wetland. So if you know you're going to trip a threshold, you're not going to have an exemption, and you're going into MEPA, one of the things that will be required is an RMAT analysis. They'll require that you use the RMAT tool and come up with some climate projections. And depending on the project, they may ask you to do analysis for heat or for extreme precipitation, for coastal flooding. And those go in as part of your MEPA submittals, either at the environmental notification form level, and then if it's a higher level of review, at the environmental impact report level. So those are just kind of early considerations when people are starting to think about the project and where it might be headed. Those are something that's important to think about. Next. Another one is, will your project involve MassDOT review? So are you working on a project with a bridge or culvert crossing that's under MassDOT control? Is it on a highway or an area that they will be looking at? They tend to require a higher level of detail. They want more specific modeling done, and they have specific preferred models that you see here, HEC-RAS 2D or SRH 2D. And they also have their own set of considerations for climate change. So RMAT looks at climate change, and that's tied to MVP or to MIPA, but MassDOT has their own method of doing things and their own analysis that they would like to see. So if you're in a project that may need MIPA review and MassDOT review, then you may need to do multiple sets of analyses or have some initial conversations about whether there could be an overlap or one method might be used over another. Next. So another set of involvement that might come in is FEMA. As Rex mentioned earlier, you can kind of see it in the white hatched line on this image on the left. That's a FEMA floodway. So if you have a project, it's like a dam removal or a culvert project in a FEMA floodway, you'll have to look at doing a no-rise analysis. And there's a prescribed methodology that FEMA likes to see for those and a prescribed reporting format. So again, this could be a different set of analyses. If there is no rise, then a no-rise report will go to the local floodplain authority, which is at the town level typically. If there is a rise due to the project, then there's a different step, which involves what are called LOMRs, which is a letter of map revision. And those documents have to be submitted to FEMA directly. One other note is that they will provide their models as part of this process to anyone. There may be a fee involved for the data or for them to provide that to you. But that's just another kind of factor to think about in terms of scoping and planning for these types of projects. And not every site will have a FEMA floodway. Sometimes it's a little bit buried in. It may not be shown on a map distinctly, so you may have to look at the FIS as well. Next. So just an example, this one's a little bit of we kind of threw it all at you. So what if you have a highway culvert replacement that's in a FEMA floodway that's funded by an MVP grant? So 3 layers of complicating factors. And the question we want to answer is, what size culvert will pass the 50-year flood without overtopping the roadway? So the 50-year flood was determined to be the design storm for this site. So how do we do that? So we need the hydrologic model to help give us that rainfall runoff connection to estimate what that 50-year flow looks like. So MassDOT has their own preferences for what methodologies you might use for that, and FEMA has their own preference. So you may need to look at things in multiple ways to satisfy all of the agencies or groups involved. Same goes for future projected flows. If there's an MVP grant, they'll want you to potentially look at the RMAT tool, whereas MassDOT would want you to use their CCI calculation. So that would be a situation where MassDOT's maybe the less flexible one in this case. So it may be a question to MVP to say, hey, can I use the CCI calculation to satisfy my projected future flows, or do I need to do both? So those are just good considerations. And when it comes to the hydraulic model, FEMA has their own preference for no-rise analyses as part of their standard methodology, and then MassDOT has their own preference. So there's multiple factors that can come into play when we're looking at these types of projects. Next. So I just want to give 2 examples. This is kind of the practical side of things. One's a culvert replacement, the other is a dam removal. And this is a GZA project. We'll keep it anonymous, but this was replacing an undersized pipe arch culvert that had some signs of structural deterioration at a roadway crossing. And the ultimate goal for this project was to reduce the flooding occurring upstream and to improve resiliency for water and transportation infrastructure. So trying to keep things within the banks of the channel and also not overflowing the roadway in this location. So this project included consideration with RMAT and also had Mass Highway or Mass DOT review rather. There were also a series of different permits and review approvals, including submittal of a MHC, a Mass Historical Commission project notification form, a Wetlands Protection Act notice of intent with the locals, and then also an Army Corps Section 404 permit for the work within the stream. So those are some of the considerations that had to go into scoping and the design process and permitting. Next. So we thought it might be useful to kind of lay out, what do we do in each of these? So as a consultant, what are we starting from? So we're starting from public data like FEMA data. We're looking at LIDAR for terrain or topography. We're also looking at gauge data for flows. And then beyond what's available publicly, we would do some site-specific data collection. In this case, we did geotechnical borings to look at the subsurface. Since we're replacing a culvert, it might be important to know what the foundations might need to look like or what it would be founded on. We also needed site-specific topographic data, which helps inform the model, but also helps inform the design and how the new culvert will sit in that setting. And then also, because of permitting, we needed to look at the wetlands, waterway, and also the habitat present in this area. And as part of this work, we did HEC-HMS on the hydrologic side. We also projected future flows. And then on the hydraulic side, for a culvert replacement, we were doing 1D HEC-RAS. Next. So another example is a dam removal that we're currently working on. And this is a former industrial dam where we needed to reconnect the upstream and downstream floodplain that were separated from the impoundment behind the dam to below the dam. There were some challenges here. We had a constrained stream within walls. There were basically walls downstream along the channel. We are in a FEMA floodway, so we needed to do a FEMA no-rise analysis. And because we didn't want to have head cutting continuing upstream, we needed to look at grade control methods. And in this case, we ended up using a riffle, which was meant to help provide grade control, but also to help with fish passage measures. And in this particular site, there was some pressure to limit sediment movement. There was potentially 30,000 yards of mobile sediment, which kind of got the regulators a little bit nervous. So we looked at kind of some innovative techniques to figure out how we might be able to stabilize this in place and reduce sediment transport. We're restoring sediment transport along the channel by removal of the dam, which is desired for riverine processes, but we wanted to kind of limit how much might be moving down. Next, Rex. So this project had an early drawdown. So this is the same impoundment that's behind the dam, but we did an early drawdown, opening the low-level outlet to help stabilize things in place. So when we're looking at the modeling for this project, there was initial modeling as an impoundment, and then there was additional modeling done with that kind of that viewpoint of the gate being open and the stream in place. You can see in the profile that's here, you can kind of see that green is the channel bottom. It's kind of erratic because it's kind of sinuous through the impoundment. And you can see the red, which is with the dam in place, and the green is the bottom after the dam's been removed and we have a pilot channel through the dam. The darker blue on top is the water surface pre-dam removal, and the one just below that is post-removal. So for this one, we used some similar public data sources from FEMA and from publicly available LIDAR. We did a lot of site-specific topo. This was a pretty large impoundment, and we had the channel as well. So there was a lot of work done on site. Also detailed bathymetry and a bunch of sediment sampling. We also did the typical wetland delineation and habitat assessment as part of the field data collection. And on this one, we looked at a gauge analysis and then a HEC-HMS model on the hydrologic side, sorry. And then again, because we had kind of different folks we needed to please during the regulatory review process and during the design process, We did a 1D HEC-RAS model for the FEMA no-rise, and then for our work, we wanted to have a 2D HEC-RAS model to provide a lot more of a detailed analysis about how things were going to move post-dam removal. Next. So those are just a couple examples. Another thing, for us is kind of the takeaways of what makes a good or a bad model. What are the limits of a model? So models are only as good as the inputs and the modelers themselves. If you don't have data from reliable and accurate sources, if you're starting with bad data, you're not going to have a good model. You are only going to have a model that represents what you put into it. You need the modeler to be able to make informed selection of what data is most appropriate to include. It's great if the modeler, or at least folks on the team, can visit the site to understand the real world conditions. And sometimes there's things that aren't really represented well in a model, or you can't understand until you see it. So it's important to have that kind of boots on the ground look at the project site. And then finally, calibration, if you can do it, can be used as a check for accuracy on the model. And it's a really important step. But, a model is really just a tool and a representation of something that's occurring in real life, because we can't go out and, you can't go out and build a slosh tank very easily to represent an entire river corridor. So we need to do what we can to represent it through modeling. Next. So some kind of takeaways and considerations. We've talked a lot about both the H's, all the models that are available, the types of projects, and when you might use these models. But once you have a model established, what do I need to think about when I'm looking at the model results and output and the reports that come out of these projects? And we thought that might be useful as well, as you may be the reviewer on these projects. So first, I think it goes back to basics. What was the goal of this, and what was needed for the intended purpose? Did you have a requirement to use a certain methodology? Did they do so? Did they need to consider climate change, and was that included? Considerations like, what did they have available for information, making sure it's clear where were their data sources from, and was calibration used? What was the calibration data that was used? And then when it comes to the reporting or the H&H memo, do the results show the info you need? Is it clearly represented? Are there existing and proposed condition water levels, since that's a primary thing you need to see often? If you're thinking about things like fish passage, did they also include information on velocity, since that can be an important factor, as well as slopes? Are the results clearly presented? Are there good tables? Is there a good summary up front, so that you don't get lost in the modeler's 10 pages of this is all the methodology I did to get from point A to point B? Is there a quick summary that tells you what they did and what the results are, and what do those results mean for the project going forward? Those are just some basic considerations. Next. And also, a lot of times it's more than just us. It's more than just the technical team on the consultant side, or the project team or project proponent. A lot of cases we need to communicate that information to the public, and it's really hard to communicate something so technical. So understanding the audience is key. Is how do I boil down something very technical to being something that the public can understand? And the answer is pictures. A lot of graphics can be very helpful, and clear graphics that are well labeled at a good scale so they're visible, and then also having someone available to kind of walk through those results with the public. So having public meetings or providing online resources. And then on some of, especially with dam removals, there ends up being stakeholders, and often they may be public meetings or some intent for public input, especially if it's a public site. So gathering things like feedback and having public forums to address questions or concerns, and then providing updates on the project and its timelines can go a long way to kind of helping folks understand where everything is at in the process, what things will look like at the end of the project. Those are all considerations as you move forward, kind of from point A to point B. All right, so we're down to the end of it, and then we'll open it up to questions. So just some takeaways. We went through a lot of terminology, and we'll have the slides available. We're happy to go back to any slides if you have questions on certain things, but we kind of broke it down to the basics. What are the two H's and what do they mean? What are the data sources that are out there publicly? What are the types of software we can use for these models? And also, what is the level of effort and what do we need to do for an individual project? And that depends on the purpose of the project, the stage, how complex the site is, what the regulatory review requirements might be, especially when it comes to needing to do climate projections or specific types of models. And then the bottom line really comes down to what data is available or can we get, and what funding and budgetary considerations there are in terms of what we might be able to afford to do for modeling at that stage of the project. So I know that was a lot and you're probably a little glazed over. I hope you had lunch to refresh while we were presenting, but we'd be happy to open it up to the group and take any questions, go back to any slides, talk about big pictures or little pictures. If you've got a site in mind and you have some questions, we're happy to take those as well. And I think I'm going to have Courtney said she might moderate if we had questions that came in the chat.
There's no questions in the chat, but I will ask a question to kick us off while people formulate theirs. So sometimes we are able to get localized data if there isn't any stream gauges or something like that. In what format is it most helpful to have that data? Like, what types of information do you need when we send out a survey that says, remember when it rained July 2023? Like, give us your information so that we can calibrate this model. Give us any tips on what that might look like so that it's the most useful information for you all.
I'll let Rex take a first stab at that one, but I know we have a project where we just did that, where we asked the DPW director and said, hey, we have data from Irene. Irene is saying that it looks like that this particular bridge might have overtopped. What did you guys see on the ground? And, if the storm hits in the middle of the night, there may not be good on-site data, but DPW is the one that's going to get the first call. So they're always a good resource, and any of that info can help us in terms of calibration. But Rex, I'll let you unmute and answer in the technical way.
I think just focusing on specific storm events that are feasible. So, if we know we have the rainfall data for Irene, right? Then we want to ask them specifically, like, oh, do you know if there are any depths for this bridge for Irene? I think just having it targeted. But I think Chad might also have some input.
Sure, yeah. When we're thinking about flood flows, high water marks and anecdotal information is really key. That project that Jen was just mentioning, we had an initial model run that had the bridge overtopping, and when we were able to talk with the DPW folks that said, no, it came up to the bottom chord of the bridge structure, but it didn't overtop, that let us calibrate our model better and generate more realistic results. So that was definitely key. But other data collection might involve the low flow kinds of issues, particularly when habitat restoration is a part of the project goal. That's important. So if project specific stream flow data can be collected on the basis of really even just setting up stream staff gauges and developing tables of data that just, on a particular date, at a particular time, this was the depth of flow on the flow gauge, on the staff gauge, and that kind of information can be developed into a long-term data set. Now, in and of itself, that may or may not be sufficient. It might be necessary then for someone to go out and do a cross-section of the stream and get some additional data so that those depths can be transformed into an estimate of flow, and then that time series of depth data can also be viewed as a time series of flow rates. But those are all very good site-specific data sets that can help a modeler really refine his or her model.
And I think Robert chimed in too with photos, and photos are always great because that's another one we can look at, especially in this date and age with digital photos, because they'll have a timestamp on the file. And that's really helpful to us as well for things like looking at low chord of a bridge or overtopping. We may be able to glean, a good bit of info for a file or from a photo file or series of photos over time. And yeah, but staff gauges are great. Like if going into a project or planning for a project, if there's something that's cheap and easy to install and you have a nosy neighbor or just a great neighbor that lives next door to the stream and is there all the time and is willing to go out once a day, once a week, whenever there's a big storm and take a note about what that's at, that too can be useful for calibration over time, especially since when you think about these projects, unfortunately, they don't happen overnight. It's often 2 to 5 years before a project like this really comes to completion. So over that time span, it can be useful to get some data. Looks like Chris has his hand up. If you can unmute him.
Thanks for that presentation, guys. It was really helpful. I think you did a really nice job summing things up. Just for the organizations here who might be interested in doing some of that stream gauging, do you have any advice on siting the gauge? Because I know it's important that you put it in the right spot. You're not getting bad data.
So I could take a quick shot at that. Oftentimes, the upstream side of a culvert can be a useful place for a staff gauge. There's 2 reasons for that. One is because the culvert makes it easy to understand the geometry of the conveyance structure. So if your stream gauge, if your staff gauge is out in the middle of a sort of just unimpeded stretch of stream or river, then understanding the cross-sectional area of flow at any particular flow depth can be difficult. You really need to have a good cross-section survey to have a hope of transforming depth into flow rates. But if you're at a culvert, the geometry is very well defined. It's a circle and it's 36 inches in diameter, or it's a box culvert and it's 4 foot wide by 6 foot high, or whatever. So that's important and can be very helpful. The other reason that it can be useful to put a staff gauge, at the upstream side of a culvert, is because it's just convenient, right? You can affix it to a head wall, and that is a place where it's less likely to get washed out if there's a big flood. And it's also easy to get to, right? It's safe. You can kind of just walk down the road embankment and lean over and take a look and get your measurement and write it down, and nobody has to get in the water. And the harder it is to get to a staff gauge, the less likely you are to get, consistent periodic data. So that might be those are some of my thoughts about possible staff gauge placement. Other folks may have other thoughts as well. A spillway on a dam, that's another great place to put a staff gauge, because there are reasonably simple equations that can be used to transform depth over a spillway weir of sort of a known width and shape to a flow rate. So, if you're looking at removing a dam, a staff gauge right at the pond itself, in any kind of easily accessible point on the pond can be used reasonably efficiently to transform depths into flows.
I think the only other thing I'd add is if we're doing it at a road crossing like a culvert or a bridge, is just making sure you get permission ahead of time and that there's a stakeholder agreement between whoever it is, whether it's town, especially if it's a state agency that owns the infrastructure, just making sure everybody's okay before you go and attack it or try to secure funding to do it and then find out that they won't let you. So it's good to have everybody involved from the get-go.
And we're happy to take any other questions, either, just shout them out or in the chat. But we recognize it is a Friday afternoon, and we are under no in no way looking to keep everybody here till the end of class. So please, whatever we can do to answer your questions, that's great. But if we've covered the things that you wanted us to cover, we are happy to have done so, and we will follow up with all of the resources that we promised after the meeting.
And I should point out too, in that I think we had our email addresses. So if there's something you don't want to ask in public, but you might want to follow up, we're happy to answer questions as well, if we can. But just if you don't want to ask in public, we understand.
That looks like it. So
I'm
yeah.
so surprised. This group has so many questions usually. So, I would say it is Friday afternoon and there's a lot going on right now. So I want to say a special thank you to GZA for pulling this together and Courtney for kind of guiding this project forward. We will be pulling these resources together for you all and looking for your input as well. And did we cover enough? And, or were we missing something? What else did you want to learn? So it's always just a work in progress. And if perchance you get off this call and you say, oh, wait, I should have asked that question, just go ahead and send us an email. You can send it directly to Robert because I know you all have his email, and then we'll make sure to get that over to the team so we can get answers for you all. So again, thank you all for coming this afternoon. This is a great presentation. I love the next level that it brought us to for H&H Understanding, and I look forward to working with you all soon.